Hello, Year 10. This one should be a quick one in terms of the theory, but I'm going to take you through the exam question afterwards. So if you get stuck on the exam question, please watch the end of the video where I actually go through the answers and explain why. This will be the first proper full physics lesson on this topic. There was some overlap before. Now I'm going to go straight into the PowerPoint. Okay, so we're doing about generators today. Now the first part here says give examples where we get AC and DC, and can you sketch a graph of each one? Well, we should know, first of all, where's my pen gone? There it is. First of all, if I draw, let's start with DC, and then we'll do AC below it. So if you want to have a go, just pause the video now before I get onto it. Well, a DC looks like this, direct current. So here's the positive side, this is the voltage, here's the negative side. Direct current, this is time, will stay either always positive or always negative. If you've got a really steady direct current, the line will be completely straight, but that doesn't necessarily have to be. Now, give examples, well, your mobile phone. So mobile has one. Any battery or cell, anything that runs, anything that you don't have to plug into the mains. So if you use something like, I don't know, a torch, anything that's run by batteries, it will be direct current. So let's have a look at AC, which stands for alternating current. Hopefully you remember it looks a little bit like this. Sorry that I overlap the text. So your voltage goes from positive to negative. And this is time. So we go from positive to negative to positive to negative. So an alternating current, the voltage alternates between positive and negative. Now usually that is at a constant rate, and we call that the frequency. You need to know specifically anything that is plugged into the mains uses alternating current. So your plugs at home, your plug sockets are alternating current. Now you need to know that the mains, oh that is not, the mains voltage, I don't know why I can't write for some reason, 230 volts. The mains voltage is that, and the frequency is 50 Hertz. Okay. If you can't remember, you're going to have to go back in your notes and have a little look. But we're going to move on now. This is a quite important law. Now we talked about passing a current through a wire, and that wire then feeling a force if it's inside a magnetic field. So we call that the motor effect. So if we had a current flowing through a wire, it would feel a force inside another magnetic field. What this is saying, so I'll read it out first and then I'll explain it. So when in a magnetic field, if moving electrons can make a wire move, can moving a wire make electrons move? Well, the answer is yes. So we're actually doing the opposite. This is called Lenz's law. An induced electromotive force always gives rise to a current whose magnetic field opposes the change in the original magnetic flux. That is a very sciencey definition. All this is saying is if you put a coil, let's say you've got a coil of wire and you put a magnet inside that coil, you'll create a current. So let's look back at motors. If you have a current flowing through a wire and it goes into a magnetic field, it will feel a force. Now we are saying if you have got a wire and you push that wire into a magnetic field, you can create a current. I'll show you what I mean. So now we just need to know before I actually do the simulation, if you move a conductor into a magnetic field, this will induce a current. We call this electromagnetic induction. Just like when we talked about the nails before being an induced magnet. because it was put into a magnetic field. Now we are forcing a conductor to move through a magnetic field. So, and this is called electromagnetic induction as well. If you connect to the if you connect this to a circuit, okay, we call this the generator effect. If you've ever had a windy torch, and you had to wind it up for it to turn on, you were using the generator effect. You had a coil that was inside a magnetic field, and you forced that coil to spin around in the magnetic field, which then generated electricity. Now, before I go into these questions here, so let's make this a little bit smaller and zoom in because we can kind of see the answers there. Right. So we've got a few questions. And I have got a nice little simulation for you, because I can't show this to you until we get back to school, but luckily we've got this website, phet.colorado.edu. It's got loads of really good simulations on, loads of good physics ones as well, if you ever need to have a look. So, we have got a coil of wire attached to a bulb and a voltmeter. Now if you look, this magnet stays still, nothing happens, but if I move the magnet towards the coil, you can see that the voltage gradually increases or gets larger. If I move it away, notice that the stronger the magnetic field is, the more voltage there is. That's not entirely true. It's to do with the change in the magnetic field, but for now, look at the field lines. Yeah, the more field lines that cut through this coil, the higher the voltage is. So if I cut the field lines through the coil quite quickly, yeah, so we're a really strong magnetic field here now, and then do it the opposite way. So I can move it really quickly over here and nothing will happen, and I can move it really slowly into here and it'll be very strong. Yeah. Now let's have a look with another coil that's got less coils. So if I move it in like that, if I do it with less coils, you see it's not quite as bright. Then I'm going to flip this. So we'll go back to one coil again. From the north side, going back to the original, notice that if I push the north side in, it goes negative, and I pull it back out, it goes positive. If I flip it, I push the south side in, the opposite happens on the voltmeter reading, right? Let's answer these questions. What happens when the wire is moved into a magnetic field? Well, we are moving the magnetic field into the wire technically, but it's the same thing. What happens when the wire is moved into a magnetic field? A current or a voltage is induced. I would stick with the voltage being induced, because if this isn't a complete circuit, there won't be a current. If it is moved out again, so let's move it in, the voltage goes that way. If I move it out, it moves in the opposite direction. The wire is stationary in the magnetic field. Well, if I leave it stationary like that, nothing happens. The wire is stationary, the magnet is moving. Well, it's exactly the same thing. You will get a magnetic field. Sorry, you will get a voltage induced. Changing the speed at which you move the wire in and out of the magnetic field will change the voltage. Yeah, you see that? So I move it in slowly, move it out quickly. So, here you go. The faster you move, the higher the current is induced. Now, what is happening actually? The movement of the magnetic field across a conductor induces a potential difference, and the important thing is that the field lines have to cut through that conductor. Now, the potential difference makes a current flow if it is part of the circuit. Now, there's a few factors we need to know. If you introduce a bar magnet into a coil, there are factors that affect the potential difference that is induced. If you have a stronger magnet, you have got a higher potential difference. If the wire has a higher area, or the coil I should say has a higher area inside that magnetic field, you will have a higher potential difference. If you move the magnet faster, you will have a higher potential difference. So let's now we've gone through the notes. So let's have a look at the exam style questions. So here they are, and I put them open in OneNote. Okay. Let's get my pen out. Question 1. What I'd recommend you do, by the way, is I'd recommend you either pause the video and go away and try this yourself, or have a go at it, and then if you get stuck, unpause the video so I give you the answer. Question 1. The figure below shows a coil and a magnet. So there's my coil. I'll do it in red. And there's my magnet. An ammeter is connected to the coil. That's very nice. So this is a full circuit. The ammeter has a center zero scale. So the values of current going in either direction through the coil can be measured. That just means, as you see before, as in on the simulation I just had, you saw the needle went positive and it went negative. That's all that means. A teacher moves the magnet slowly towards the coil. Explain why there is a reading on the ammeter. So this is an explain question, and you can see it's a 6 marker. Well, if I just got a block of wood and moved it towards the coil, nothing's going to happen. So why? First of all, the reason why the ammeter moves is because, well, sure, I'll write it up here. There is a changing there is a changing magnetic field. This actually gets you 2 marks. Okay, you get a mark for saying there's a magnetic field, but if we go back to the simulation that I did before, just very quickly, right, if I leave it in there like this, there is a magnetic field here, but nothing's happening. Why? Because the magnetic field is not changing. As soon as the magnetic field starts changing, that is when you get a reading on the ammeter. So there is a changing magnetic field. That is 1, 2. Now, the next thing is that magnetic field, I said before, the magnetic field has to cut through the coil. The magnetic field. So just see, this is one sentence. I'm bullet pointing it so you see where the marks are. Sorry, that. We'll rub that out. So there's a magnetic field that cuts through the coil. Yeah, that's a mark. Now, that's good. That's why this is happening. So this is what is causing it. But on the coil's end, why does that work? Well, we said that a changing magnetic field that cuts through a coil induces a potential difference. That's a really important word. If you don't write induces, the chances are you're going to lose your marks. So, a potential difference is induced across the coil. Now, you can say the potential difference is given to the coil, maybe, but I would recommend always using this word, because this is the most important key word right there, induced. If you don't say induced, the examiner might just not give you a mark. So the potential difference is induced across the coil. Now, you heard before in the earlier definition, this was called the electromotive force, EMF. For now, just if you ever encounter the words EMF or electromotive force, just count them as the same thing as potential difference. Okay, so this is the generator effect, right? We've said that the changing magnetic field, 2 marks, it cuts through the coil, good, a mark, and that potential difference is induced across the coil. Well, how does the ammeter work? Well, this is a complete circuit. If this was broken here, the ammeter wouldn't work. So you have to state the obvious. The coil forms a complete circuit, or do you know what, there. So this is a end of sentence. there is a complete circuit. So a current is induced, or so a current flows. So a current flows. I like the word induced, so I'm going to use it. Again, probably the most important word in this whole question right there. To be honest, the word induced is pretty important in most of the topic. So there's mark, mark, there's your 6 marks. Okay, let's move down a little bit. The table below shows some of the actions taken by the teacher. Complete the table to show the effect of each action on the ammeter reading. Well, the question said before, so let's go back to what did the question say, just so that we, because it's referenced in the, so the question says, a teacher moves the magnet slowly towards the coil. So the teacher, he moves the magnet slowly towards coil. That's important because it's referencing the question before. Well, let's see. If he holds the magnet stationary and moves the coil slowly towards the magnet, well, is that not just exactly the same thing? If the magnet is, if the coil was still and I move the magnet towards it, or if the magnet was still and I move the coil towards it, they're both the same, so, well, it should have the same reading on the ammeter. So I'm going to say the, so what happens to the ammeter reading? Well, it should be the same. You could say it doesn't change if you want to. Now, the next one holds the magnet stationary, so not moving within the coil. Well, we checked before, if we just have a magnet not moving, that means that the magnetic field is not changing, so there is no reading, or 0. The reading goes to 0. What if he moves the magnet quickly towards the coil? Well, it's still going to be the same direction as before, isn't it? But the reading's going to be greater. So I'm going to say that the reading is larger, or greater. And if he reverses the magnet and moves it towards the coil, so we're still going towards the coil slowly, which is what he did before, right? Slowly towards coil, but this time the magnet is the opposite direction. So let's say it's the same size really on the voltmeter, but it's going the opposite way. So let's say the ammeter, sorry, it's an ammeter in this question, not a voltmeter. So the reading will be the same size, but negative, or opposite, I'm going to say, just to be safe. But opposite direction. Now, let us... don't want to skip that question. Right, part C. This one should be straightforward if we remember our equations from the electricity topic. The magnet moves so that there is a steady reading of this, an ammeter, for 6 seconds. So just in case, I'm going to do this thoroughly, they've given me an ammeter reading, so I know that that is a current, so I'm going to write that down. For 6 seconds. Well, that's a time. Calculate the charge that flows through. Well, Q is the charge, and we need to calculate it. They are the 3 things that they have given us. So hopefully I remember an equation for this, right? And I have to give a unit at the end. So if you're completely stumped and you've forgotten your equation, hopefully you remember the unit for charge flow is coulombs, capital C. Now, I remember that a current is a rate of flow of charge. Yeah. A current is a rate of flow of charge. So my charge flow must be, well, how is a current, but how long has that current flowed for? Did I That will give you my charge. You can either rearrange this, or you could put it into your equation triangle like that. So Q equals I times T. Well, I is 0.05 and times 6, and that gives us 5 times 6, 30, so 0.3, so 0.3 coulombs. 1 mark, by the way, 1 mark is reserved for that unit there. So if you got that unit, you get a mark, even if you didn't do any working. 1 mark will have been for getting the correct equation and putting the values in, like I did here, and then the final mark would be for getting it correct. Let's have a look at the next. My question 2. So this is actually moving on to something that we haven't done properly because we can't do it in school, but generators. Now we can tell this is a generator because it has a slipped ring. Before we did the motors, motor equals a split ring. Okay, and if you looked at part of the motor would have a section like this, where it's all coloured in, and like that. It'd be like a rotation, and it would say there would be a brush on each side, and this would spin, but it would cause the brush to go onto the opposite part of the split ring, which causes the current to alternate, which allows your motor to spin really quickly. Now, this is a slipped ring. So you see here, this ring allows this wire, this part of the wire here, to stay in contact with it at all times. And this one, this ring here, allows this wire to stay in contact with it at all times. But the red one will not touch the blue one, and the blue one will not touch the red one. So you can use this to create an AC current. This is an AC generator. Now, a potential difference is induced between X and Y, because what we're doing, we're forcing this to spin around, yeah? Someone is coming and someone is spinning this by hand or on a bike or however it is. And that's forcing this to spin, and it is forcing a current to be induced, or a potential difference to be induced. And we call this the generator effect, okay? Because we are moving the coil and generating a potential difference. What does AC stand for? Well, that's alternating current. Name an instrument that could be used to measure the potential difference. This one, you should be able to do this one in your sleep. That should be a voltmeter. Now let's move down a bit. Graph 1 shows the output from the AC generator. Oh, look. You can see it looks a bit like my drawing from the start of the lesson. One of the axes on graph 1 has been labelled. Potential difference. What should the other axis be labelled? Well, this should be time, shouldn't it? Yeah, time. The direction of the magnetic field is reversed. Graph 1, draw the output from the AC generator if everything else remains the same. Well, remember when we had the magnet before, and we had our voltmeter, right? And it had a little arrow, and when we pushed the magnet with the north in that way, the arrow flicked that way first, and then when we swapped it around and we had the south, it flipped the other way. I'll show you again just in case you forgot. Where's my mouse gone? There it is. Yeah, so push it in like that. See, the north goes towards the negative, and then when I flip it, the south goes towards the positive. Yeah. So if I flipped my magnetic field, the potential difference would flip, okay? But everything else should remain the same, because it says that. Yeah, everything else remains the same. So if I was to draw it, now you'd have to take care making sure Yeah, oh, I messed my hand up there. Doesn't matter, I'll keep going. Right. So literally just the peaks and troughs sort of get mirrored in the time axes. Just basically flipped it. The number of turns of wire on the coil is increased. This increases the maximum induced potential difference. So we are not... Oh, sorry, I'll finish the question first. State 2 other ways in which the maximum potential difference could be increased. Well, we can't use turns of coil on the wire. It's been said. You can't use it. Even though that's one of the ones that's the obvious one. Well, what is a better way to get a higher voltage? Well, you should really think about if you had a windy up torch. If you wound the torch faster, it would be brighter, right? So let's say increase the speed of the coil. This is happening because you are changing that magnetic field quicker. The quicker the change of the magnetic field, the higher the voltage that's induced. Now, again, another obvious one that we've done that relates to the motor effect as well. If you increased, or do you know what, I'll say get stronger magnets. Yeah, that's perfect. Now, another one you need to remember, because they might ask you about it, if you increase the area of the coil, okay, that is the area of the coil that is inside the magnetic field, that increases it, and that's a new one that we've learned today. Now, that is the questions done. Please email your notes and your exam question to me, and any questions that you've got about this topic, and I'm happy to help.